Okay, so we've got 4.6 is on the topic of color. We've got spectral distribution and color might seem like two names for the same thing, but they are distinct. Spectral distribution is a purely physical concept where color describes the human perception of the spectrum. Um, color is closely connected to the physiology of the human visual system and the brain's processing of the visual stimulus. So, although the majority of rendering computation in PBRT is based on spectral distributions, color must still be treated carefully. For example, spectral distribution at each pixel in a rendered image must be converted to RGB color to be displayed on a monitor. Performing this conversion accurately requires using information about the monitor's color characteristics. Renderer also finds color in scene descriptions that use it to describe reflectance and light emission. Although it's convenient for humans to use colors to describe the appearance of modeled scenes, these colors must be converted to spectra if a renderer uses spectral distributions as part of its light transport simulation. Unfortunately, doing this is an underspecified problem. A variety of approaches have been developed for it. One is implemented in this book. Tristimulus theory of color perception says that all visible spectral distributions can be accurately represented for human observers using three scalar values based on the fact that there's three photoreceptive cone cells in the eyes, three types, each sensitive to different ranges of wavelength. It's been tested in numerous different experiments since the 1800s and led to the development of spectral matching functions. There are functions of wavelength that can be used to compute a tristimulus representation of a spectral distribution. So integrating the product of a spectral distribution with three tristimulus matching functions gives three tristimulus values VI. This is integrating the spectral distribution times the, what is the MI is the function of wavelength that gives you the color or something. Matching functions thus define a color space, which is a 3D vector space of the tristimulus values. The tristimulus values for the sum of two spectra are given by the sum of their tristimulus values, and the tristimulus values associated with the spectrum that has been scaled by a constant can be found by scaling the tristimulus values by the same color. Note that by these definitions, tristimulus values for the product of two spectral distributions are not given by the product of their tristimulus values. Tristimulus values for the product of two spectral distributions are not given by the product of because the tristimulus values makes it down to something more limited, I guess. Okay, may not give, using RGB may not give accurate results, and there's more in that other section. Okay, so looking at XYZ color matching curves, so you can take as a function of wavelength, you can get a point in XYZ space that represents that color based on these curves. I've actually been messing around with this. So what's interesting is when you do like spectral rendering, there's a couple different ways you can do it. You can do like path tracing style like accumulation where you just average in this like XYZ space, or you can basically keep like a wavelength histogram. So essentially, it's like just keeping counts of intensity across that spectral distribution, like what they're talking about, and then at the end, like converting that to something in RGB. The CIE standards for experiment were determined after a series of experiments with human test subjects to define the XYZ space. The device-independent color space, which means that it does not describe the characteristics of a particular display or color measurement device. So given spectral distribution S of lambda, its XYZ color coordinates X, Y, and Z lambda are integrated its product with the spectral matching curves. The Y tristimulus curve was chosen to be proportional to the V spectral response curve used to define photometric quantities such as luminance. Where was V coming from?
I think they just introduced V.
Okay. Okay, so we got a 3D plot of the curve in the XYZ space corresponding to the XYZ coefficients for a single wavelength over the visible range. So single wavelength of light. Coefficients for more complex spectral distributions therefore correspond to linear combinations of points along this curve. Okay, so that this is you've got your blues are kind of the lower wavelengths, those are and down like 400s and things, and then up through reds going into like 700 and stuff like that. So that's interesting. So I guess that's these curves visualized as a 3D plot. That's interesting. Yeah, 360 to 830. So I guess they are. Actually, somebody gave me this code. I was not sure that I wasn't aware that it came from here. But yeah, so there's some curves that give you you basically you've got a function of lambda, it was the frequency or wavelength rather, and you get a point in XYZ space, and you can you can average in XYZ for spectral rendering. So spectrum at XYZ computes the XYZ coefficients for a spectral distribution. Okay. Spectra. So
Yeah, I guess this is just above
integral.
integral.
Going through the code here, yeah. Because we're kind of also useful to compute XYZ coefficients for sampled spectrum. Okay, I missed this chapter, so I may not be 100% up to speed on this. So we have sample spectrum values Si at wavelengths lambda I, and associated PDFs. So I guess that's getting into implementation specifics there. So color can be separated into lightness, which describes how bright it is relative to something white, and chroma, which describes relative colorfulness with respect to white. One approach for quantifying chroma is the XYZ chromaticity coordinates, which are defined in terms of XYZ color space by these equations. The two of them are sufficient to specify chromaticity. Kind of like a barycentric thing almost. Considering just x and y, we can plot a chromaticity diagram to visualize the values. In this figure here. Spectra with a light at just a single wavelength, pure spectral colors lie along the curved part of the chromaticity diagram. Part corresponds to the XY projection of the 3D XYZ curve that was shown before. So all the valid colors lie inside the upside down horseshoe shape. Points outside the region correspond to imaginary colors. Colors you can represent in this space. So the XY color space separates the chromaticity from the lightness. Uses X and Y chromaticity coordinates from Y lambda and Y lambda from XYZ, since Y of lambda matching curve was defined to be proportional to the luminance. So it makes limited use of X, Y, Y colors, and therefore does not have a class, but uses a 0.2 for representing that chromaticity. Okay, so RGB is more commonly used than XYZ. Most things just deal in RGB. RGB color spaces, colors are represented by a triplet of values corresponding to red, green, and blue colors, often referred to as RGB. RGB triplet on its own is meaningless, must be defined with respect to a specific RGB color space. To understand why, consider what happens when an RGB color is shown on a display. The spectrum that is displayed is given by the weighted sum of three spectral emission curves, one each for red, green, and blue, as emitted by the display elements, whether they are phosphors, LED, or LCD elements, or plasma cells. The next figure here plots the red, green, and blue distributions for LED and LCD displays, and notice they're very different based on just the emission spectra of the display. So interesting. Okay, these are showing a uniform color, and then showing the resulting spectral distribution in terms of wavelength. That's cool. So if it displays red of lambda, green of lambda, and blue of lambda curves are known, the RGB coefficients for displaying spectral distributions S of lambda on that display can be found by integrating S with each curve. So red is integral of red times the spectral distribution, so forth. Same approaches were used to compute the XY or XYZ values for spectra in the previous section could be used to compute the values for those integrals. Alternatively, if we do have X of lambda, Y of lambda, Z of lambda representation of S of lambda, it's possible to convert the XYZ coefficients directly to the corresponding RGB coefficients. So, for example, computing the value of the red component, it's like this. We're looking at these integrals in terms of those XYZ functions of. Okay. And integrals of the products of an RGB response function and the XYZ matching function can be pre-computed for a given response curve. making it possible to express full conversion as a matrix. PBRT frequently uses this approach to efficiently convert colors from one color space to another. So RGB class has some arithmetic operations. Addition, subtraction thing. Checks for quality, inequality, that kind of thing. Element access. Yeah. Full spectral response curves are not necessary to define color spaces. For example, a color space can be defined using XY chromaticity coordinates to specify 3 color primaries. From them, it's possible to derive matrices that convert XYZ colors to and from that color space. Cases where we do not otherwise have or need spectral response curves, explicitly, this is a convenient way to specify a color space. So there's some conversion functions. RGB color space is defined using chromaticities of red, green, and blue color primaries. Primaries define the gamut of the color space, which is the set of colors that it can represent with RGB values between 0 and 1. For 3 primaries, the gamut forms a triangle in the chromaticity diagram where each primary's chromaticity defines one of the vertices. In addition to the primaries, often it's necessary to specify the color space's white point, which is the color that is displayed when all 3 primaries are activated to their maximum emission. Maybe surprising that this is necessary. After all, shouldn't white correspond to a spectral distribution where, with the same value at every wavelength, white is, however, a color, and as a color is what humans perceive as being uniform and label as white. Spectra for white colors tend to have more power in the lower wavelengths and correspond to blues and greens than they do at higher wavelengths that correspond to oranges and red. The D65 illuminant, which is described in 4.4, is common choice for specifying the white points. Okay, so it's a certain distribution of wavelengths that it's white, I guess. Spectra for white colors. While chromaticities and white point are sufficient to define a color space, the RGB color space constructor takes full spectral distribution, which is useful for forthcoming code that converts from color to spectral distributions. Storing the illuminant spectrum allows users of the renderer to specify emission from light sources using RGB color. Provided illuminant then gives spectral distribution for RGB white. 111. Represents the illuminant as the densely sampled spectrum for efficient lookups. Okay, it's like a float of values. Okay. So it's like a histogram of 107. Okay, so that's the same as like what that D65 illuminant was doing. It's basically just a set of values that correspond to wavelengths. The intensities of the different wavelengths. Okay, so we got RGB color spaces also store a pointer to table class that stores information related to coloring or converting RGB color space values in the color space to full spectral distributions. So that makes sense that they're just kind of taking those matching curves and creating that histogram. I guess that would make sense. You would be able to build a table out of that. So we've done using 3x3 matrices, converting to XYZ. Okay. For the matrix M, transforms RGB coefficients to XYZ. Considering the relationship between RGB triplet and the white point, which is in W. Okay, so we know that this must be this proportional to the sum. And so we get some matrices that we can multiply and get the W is, what are we saying? W is. Okay, and so we have 3 unknowns, I guess, and that's wait, XYZ. Given a color spaces XYZ RGB conversion matrices, matrix vector multiplication is sufficient to convert any XYZ triplet into the color space and convert any RGB into the color space in the color space to XYZ. So we've got some conversion functions from XYZ to RGB. Easy to compute a matrix that converts from one color space to another by using these matrices and converting by way of XYZ colors. Yeah, so converting between color spaces by putting it in XYZ basically. So I guess, yeah, all right. Yeah, converting between the two spaces via XYZ. Okay. So there's some standard color spaces. There's widely used color standards. These are for like TVs and display devices, things like that. So sRGB is developed in the 90s, widely used for monitors for many years. One of the original motivations was to standardize color on the web. DCI-P3. It's another color space is developed for film projection, covers a wider gamut. It's increasingly adopted for computer displays and mobile phones. Rec 2020 is used in HDTV a lot. There's ACES 2065-1, I guess, which is primaries outside of the representable colors and are placed so that all colors can be represented by it. One reason for this choice is for it to be suitable as a format for long-term archival storage.
I keep hearing people say sRGB is supposed to be like one of the better ones, supposed to like, or I might be mixing it up where sRGB is the default and like one of those is supposed to be better.
I think, well, sRGB is kind of like one of those things that it's it's easy to mess up because it's like a like dimmer values in sRGB or what is it? It's basically to something related to like managing the response of like a CRT or something like that. I remember hearing that at one point. It was
Oh yeah. Yeah, I got it backwards. And sRGB is the outdated one because it was made for CRTs, but I forgot what one's supposed to be like the more accurate one for like modern displays.
I know Rec 2020 is used in industry for HDTV standards. I've had to look at some stuff related to that.
Although I also heard that like CRTs have a wider color range and like transition to black better than like LCDs, except for like OLEDs. Because I forget why OLEDs work better, or micro LED too.
That's a lot of that's down to the specific technology implementation by whatever company's making it too. Yeah, but yeah, there are certain technologies are better at different things. Yeah, like OLEDs are very fast at switching. Is something that's
Well,
been
like
affected recently.
the common LCD monitor, it doesn't show dim values as well as like other technologies. It just like cuts to black like way sooner. It has banding issues at darker values compared to like micro LED or OLED or CRT.
Yeah, that can also be related to like the bit depth of the. Yeah, it can be inherent to the technology. And it can also be like yes.
Yeah, it could be
There's a lot of
format.
factors there. So looking at relative coverage of those different gamuts, I guess in the graph here. So pre-initialized color spaces for each of these, and they basically just defines those color spaces. Yeah. So you'd be able to convert between those via XYZ, I guess. Okay. So why would you want to do spectral rendering? And proceeding with the description of PBRT's implementation with the understanding that it uses point sampled spectra to represent spectral quantities. This may seem natural given PBRT's physical basis and general adoption of the Monte Carlo integration does not fit with the current widespread practice of using RGB for spectral computations in rendering. We hinted at significant problem with the practice at the start of this section. Having introduced RGB color spaces, we can now discuss that further. Because color spaces are vector spaces, addition of two colors in the same color space gives the same color as adding the underlying spectra and then finding the resulting spectrum's color. It's not so for multiplication. Understand the problem. Suppose that we are rendering a uniformly colored object, something that's green, with uniformly illuminated by a light of the same color. For simplicity, assume that both illumination and the object reflectance are represented by a RGB color, 010. Scattered light is then given by a product of reflectance and the incident illumination, where the component-wise multiplication of RGB colors is indicated there. It's the Hadamard product. They call it. Yeah, that's the default for a lot of shader languages. In the sRGB color space, the green color maps to the upper vertex of the gamut represented by the colors. It's there, I guess. This RGB color value furthermore represents it remains unchanged by the multiplication. Suppose that we change the middle, or change the wide gamut color space, ACES 2065-1. sRGB color 010 can be found here in this color space. Maps to a location that lies in the interior of the set of representable colors. Same component-wise multiplication gives a different result. We have some attenuation. Has also become more saturated due to an increase in the relative proportion of green light. This leads to a somewhat bizarre situation shown in 4.24. Component-wise multiplication in this new color space not only produces a different color, it also increases saturation so severely that the color is pushed outside of the CIE horseshoe shape of physically realizable colors. Okay, it's interesting. So the ability to multiply spectral values is crucial for evaluating the interaction of materials. The same color can have very different RGB values when expressed in RGB color spaces with differently shaped gamuts. The green primary in the sRGB color gamut in the inner triangle has chromaticity coordinates 0.3, 0.6. The white dot here. And the wide gamut ACES color space, the same color has a different value used to represent it. The RGB value they used to
Look at how
represent it.
tiny blue is. There's like no blue at all. It's like an entire
Yeah,
channel.
it is interesting.
Like that's an entire channel that's just like microscopic.
Well, it's kind of the lower half because you got kind of purples and cyans. Those are also kind of they've got bits of blue in them. Like, well, that's interesting. Yeah, because it's I guess that's kind of RGB thinking, isn't it?
Yeah.
I don't know. That's interesting.
Maybe it's just like it's not 100% accurate. It's just like a high level representation or something.
Wasn't this because our eyes don't see blue very well?
Yeah, it's something to do with the
Because it's based on the stimulus of our eyes, right?
Wait, what was that thing above earlier? Like when you saw like the that I guess
Yeah.
we can. Yeah, like blue is like all sent. Is this why like people drop the blue channel and it's usually like RG like when they do like those weird bit like when they're like saving like bits? You know what I'm talking about? It's like when they do um
Oh, the gamut compression stuff.
yeah, it's
like 420 kind of thing.
yeah, I think
Yeah,
where
very
like
vaguely familiar with that.
they'll have like 3 bits for like blue, 6 for green, and then 4 for red or something like that. Like I just pulled those numbers. I know green has the most, but I've seen like weird formats where like green for some reason has 8 bits and then blue and red have like 4 or something like that.
Yeah, we can perceive green the most strongly, and then red, and then blue.
Kind of interesting correlation with color of plants. Kind of evolutionary, maybe.
I think I found it. RGB 565. That's the one where green has like an extra bit. But I think there's other ones
Okay.
that are like really funky.
Yeah, one of the really common ones for what is it, R11, B11, G10, or something like that. One of them has 10 bits. They're floating point. Yeah, what is it? Normalized floating point values. They're like 10 and 11 bits. That's one of the ones where you can kind of fit HDR RGB into 32 bits. But that does skew the colors because it doesn't have the symmetry across the thing.
Yeah.
They can actually be noticeable sometimes. Which there's like what is it, RGB 5E9 or is it RGB 9E5, where they have a shared exponent and then it's like the mantises are different per channel. There's a number of different color spaces, or well, not color spaces, but like formats for textures and things that are, in that area.
Yeah.
Okay. Ability to multiply spectral values is crucial for evaluating the interactions of materials and light sources in the context of rendering, like looking at the attenuation when it hits the surface, things like that. Same time, this example demonstrates the problem of when RGB values are used for this purpose. The multiplication operation is in some sense arbitrary, as behavior heavily depends on the chosen color space. this rendering using a spectral model is preferable even in situations where RGB output is ultimately desired. Look at this here. Additional benefits come from using spectral representations for rendering. They allow dispersion to easily be modeled in advanced reflectance models, which often have a natural dependence on wavelength to account for iridescence and thin layers of diffraction from surface microstructure. Which that's actually that's kind of what I've been looking at this stuff for is wavelength dependent refraction. To look at there's a presentation by Kawase. He's got it's called "Make Your Bokeh Fascinating," and it's kind of there's actually a whole like 5-hour course that's that was part of, and yeah, if you have like a day or two to go through that one, it's very dense, but I highly recommend it. It's got a lot of very good explanations of like how that wavelength dependent refraction happens, and a lot of different things about like lenses and things like that. Anyway, the make your bokeh fascinating thing comes well, it basically uses this idea of like a pencil map, which is it's this pre-computed lookup table that it keeps essentially the dispersion that you would get from lenses, and it uses it to weight the bokeh, like the edges of the bokeh discs. Kind of there's some color fringing that it models basically. That is dependent on that particular piece of the scene's like depth, like distance from the focal plane, basically. Because it's different whether you're in front of or behind the focal plane. Anyway, so choosing a number of wavelength samples, even though it uses a spectral model for light transport and simulation, the output is generally an image in tri-stimulus color representation like RGB. Having described how these colors are computed, Monte Carlo estimates the products of the spectra and matching functions in the form of the equation. 4.23. We briefly return to the question of how many spectral samples should be used in that sampled spectrum class. We're building up the histogram, I guess. Associated Monte Carlo estimators are easy to evaluate, but error leads to color noise in images. So we've got a situation where you've got So A is reference, B is a single image sample per pixel. Each sample only looking at a single wavelength. Substantial amount of error, variance from error, Monte Carlo estimates of the pixels' RGB colors. 4 wavelength samples, variance is substantially reduced. The color noise is still evident. So RGB is like it's like having 3 kind of. Yes, that's the way I think of it. Oh, but probably wrong. 4 wavelength samples usually sufficient since multiple image samples are generally taken for each pixel, so it can resolve. I guess so. They're looking at estimating this with a single sample or something, or rather, single sample per wavelength. So showing a scene illuminated by a point light source. Is that where only direct illumination from the light is included. So in this setting, estimator for the scattered light has 0 variance at all wavelengths. So the only source of Monte Carlo error is the integrals of the color matching functions. Single ray path per pixel, and each one tracking a single wavelength. Image is quite noisy, as you can see in B. So intuitively, the challenge in this case to be understood from the fact that renderer is trying to estimate 3 values at each pixel, the red, green, and blue, and we're trying to get that from the spectral value. well, we're trying, yeah, in B, you're trying to derive that from a single wavelength, where in C, you've got more data to look at to match it. Increasing the number of pixel samples can reduce this error, though it is more effective to associate multiple wavelength samples with each ray. Okay. Path that array takes through the scene is usually independent of wavelength, and the incremental cost to compute lighting at multiple wavelengths is generally small compared to the cost of finding ray intersections and computing other wavelength dependent quantities. So when you want to do wavelength dependent refraction, there's some equations. There's the Cauchy equations and the Selmayr equations, which are they basically just are kind of empirically matched things where there are a couple of coefficients that are in terms of wavelength that you can, yeah, it's a set of coefficients that you can use to derive the index of refraction given the wavelength. No, but anyway, that's okay. Increasing number. Blah, blah, blah. Right. So we have graphs. It's rendering time when rendering the scene in 4.25. Graph is a function of number of wavelength samples. Normalized to rendering time with one wavelength sample. Say I guess we're just looking at effectiveness of different versions here. So, computing scattering functions from too many wavelengths with each ray can harm efficiency due to increased computation required to compute spectral quantities. So yeah, if that gets too wide, you're going to do a whole bunch of wavelengths. You got to sample it a whole bunch of different wavelengths. Investigate the trade-off. We rendered from with a variety of numbers of wavelength samples, both with wavelengths sampled independently and with stratified sampling of sampled uniformly over the range 360 to 830. That's interesting because you'll see 400 to 700 pretty often too. So that's into infrared, the 830. 4.26 shows that for this scene, 32 wavelength samples require nearly 1.6 times more time than rendering with a single wavelength sample. Rendering performance with both independent and stratified sampling is effectively the same. However, the benefit of more wavelength samples is substantial. Well, if rendering with 32 is only 1.6 times more expensive. That's interesting. There's different. This is shown in 4.6. So on the log plot here, we can see that the independent samples. Scrolling does not want to go in more than like 6 line chunks. Benefit of more wavelength samples. Log plot here, we can see that independent samples mean squared error decreases the rate of big O of 1 over n, in line with the rate at which variance decreases with more samples. Stratified sampling does remarkably well, not only delivering orders of magnitude lower error, but at a faster asymptote. When we're saying stratified sampling, what are we actually talking about here? This is like using multiple wavelengths, I guess. In a more complex scene where variance in the Monte Carlo estimator is present from a variety of sources beyond wavelength sampling, we got like soft shadows, things like that. Graph of mean squared error versus the number of stratified wavelength samples. That's how many wavelength samples you have. Graph of mean squared error versus the number of stratified. Benefit falls off after 6, I guess. Okay, interesting. Efficiency versus number of stratified wavelength samples normalized to efficiency of one wavelength sample. This is, yeah. Some values that they picked. So 3 main reasons why for the current setting. It's almost a 500 times reduction in error from 8 to 32 wavelength samples. Only 2 images are two images are nearly indistinguishable. The difference in error is irrelevant due to limitations in display technology and the human visual system. Second, scenes are usually rendered following multiple ray paths in each pixel in order to reduce error from other Monte Carlo estimators. As more pixel samples are taken with fewer wavelengths, the total number of wavelengths that can contribute to each pixel's value increases. Finally, and most importantly, these other sources of Monte Carlo error often make larger contributions to the overall error than wavelength sampling. In a much more complex scene, much more complex scene with challenging lighting that's sampled using Monte Carlo. Graph of mean squared error as a function of the number of wavelength samples is shown there. And Monte Carlo efficiency is shown in section C. It's evident that after 8, it falls off. So going from RGB to a spectral representation, although converting from spectra to RGB for image output is a well-specified operation, same is not necessarily true for converting RGB to spectral distributions. That's an important task since much of the input to a renderer is often in the form of RGB colors, textures, and things like that are specified in RGB triplets. So scenes authored in current RGB or 3D modeling tools normally specify the object reflection properties and light emission properties using RGB parameters and textures. Spectral renderer RGB values must be somehow converted to equivalent color spectra, but unfortunately, any such conversion is inherently ambiguous due to the existence of metamirrors. That's a thing that would look the same under different illumination, basically. You'd represent them in the same way. Or they would look the same way with different underlying representations. How can we expect to find a reasonable solution if the problem is so poorly defined? On the flip side, this ambiguity can also be seen as positive. Leaves a large space of possible answers containing techniques that are simple and efficient. One that I saw recently was they mentioned they called it spectral upsampling. It was basically just like kind of creating values in between red, green, and blue, just by like linearly interpolating between those. Creating a new value that's like linearly interpolated between red and green, and then between green and blue, which is kind of interesting. I don't know if that's super correct, but that's very interesting anyway. So we've got spectral references of several color checker patches, and they're shaded with the associated RGB color. So those are representing a distribution of wavelengths that will give you that color that the line is, I guess. Further complicating this task, we must account for the 3 fundamentally different types of spectral distributions. We've got an illuminant spectra, which specify the spectral dependence of a light source emission profile. They're non-negative and unbounded because they can't absorb light, and they could potentially emit an infinite amount, I guess. The shapes range from smooth, like incandescent light sources and LEDs, to extremely spiky, like lasers or gas discharge fluorescent lamps, where they are very narrow band emissions. They're, if you've seen the corresponding charts for the color distribution of a fluorescent light, it's got some very sharp spikes where it's and then it's low intensity values most of the rest of the area. So, that's the rest of the spectrum. Reflectance spectra describe the reflection from absorbing surfaces. Reflectance spectra conserve the amount of energy at each wavelength, meaning that values cannot be outside of the 0 to 1 range. So they can't, if they were greater than 1, they'd be able to add light, kind of thing. Typically smooth functions in the visible wavelength range. So we're showing in 4.28 a few examples of reflecting spectra from a color checker there. Unbounded spectra, which are non-negative and unbounded, but do not describe emission. Common examples include spectrally varying indices of refraction and coefficients used to describe medium scattering properties. Okay. They have different behavior based on wavelength, and they potentially, they might do other stuff. So, like with refraction, that can actually change the direction it refracts and things like that. It'll change the IR that you use when you do the refraction calculation. So, the spectrum or section first presents an approach for converting an RGB color value with components between 0 and 1 into a corresponding reflecting spectrum, followed by a generalization to unbounded and illuminant spectra. Conversion exploits the ambiguity of the problem to achieve the following goals. So identity property, we've got if an RGB value is converted to a spectrum, converting that spectrum back to RGB should give the same RGB coefficients. Smoothness, motivated by the earlier observation that real-world reflectance spectra should be smooth. Another kind of smoothness is important. Slight perturbations in the input RGB color should lead to a correspondingly small change of the output spectrum. Discontinuities are undesirable since they would cause visible seams in textured objects if observed under different illuminance. So it's kind of a continuous type of idea. Energy conservation, given RGB values in 0 to 1, associated spectral distribution should also be within 0 to 1. So, although real-world reflectance spectra exist in a wide variety of shapes, they're often well approximated by a constant, white, black, approximately, or peaked curves with 1 or 2 modes, green, yellow. So the approach chosen here attempts to represent such spectra using a function family that is designed to be simple, smooth, and efficient to evaluate at runtime while exposing a sufficient number of degrees of freedom to precisely reproduce arbitrary RGB color values. Polynomials typically the standard building block in such constructions. Indeed, a quadratic polynomial could represent constant and linear curves as well as ones that peak in the middle or towards the endpoints of the wavelength range. However, their lack of energy conservation poses a problem that we addressed using a sigmoid function. Cool. It's like an S curve. The function strictly monotonic and smoothly approaches endpoints as it goes to positive and negative infinity. Okay. And the particular the type of sigmoid used here is defined in terms of algebraic functions, so it's efficient to evaluate. So we applied this sigmoid to a quadratic polynomial defined by 3 coefficients ci, squashing its domain to the interval 0 to 1 to ensure energy conservation. So we've got a sigmoid function of C0 times lambda squared, C1 times lambda, and C2. Representing ideally absorptive reflective spectra is somewhat awkward using this representation since the polynomial must evaluate to positive or negative infinity to reach those two limits. So we're going to handle infinity case. Yeah. All right. Begin with the definition of a class that encapsulates the coefficients of CI. Okay, we've got so given the coefficient value, it's easy to evaluate the spectral function at a specified wavelength. Sigmoid function follows the earlier definition, adds a special case to handle positive and negative infinity. The max value method returns the maximum value of the spectral distribution over this visible wavelength range from 360 to 830 nanometers. This is because the sigmoid function is monotonically increasing. This problem reduces to locating the maximum of the quadratic polynomial from 4.25 and evaluating the model there. So it's max value. Okay, so it's like at a positive infinity kind of thing. Iteratively check the endpoints of the interval along with the extremum. That's interesting. A new one. Setting the polynomial's curve to 0 and solving for the wavelength lambda. Value be ignored if it happens to be a local minimum. Yeah. How much? We got quite a bit left. All right. So turning to the second half of the RGB sigmoid polynomial, which is the computation that determines suitable coefficients C0, C1, C2 for a given RGB color. Step depends on the spectral emission curves of color primaries. Generally does not have an explicit solution. We instead formulate it as an optimization problem that minimizes the round trip error, the identity goal from before, where you want to be able to convert to and back by computing the difference between the input and output RGB values following forward and reverse conversion. The optimization goal is to do that. But yeah, basically just minimizing the error when you convert and convert back. You want similar values. So RGB functions of wavelength, describe emission curves, the color primaries, and W of lambda represents the weight point, and S of lambda C1 or C0, C1, C2 is the spectral distribution. Including the weight point in the substitution problem ensures that the monochromatic RGB values map to uniform reflecting spectra. In spaces with a relatively compact gamut like sRGB, optimization can achieve zero error regardless of the method used to quantify color distances. In larger color spaces, particularly those including imaginary colors, uses when the 0 round trip error is clearly not achievable, and the choice of the norm becomes relevant. So we could use the 2 norm. Okay, so I guess they're converting to another color space lab to do the something there. This is out of my depth. I don't. Yeah, solve the substitution Gauss-Newton approximate form of Newton's method. Optimization takes on the order of a few microseconds. They're pre-computing a table. Color cube. Worth noting that tabulation could, in principle, also be performed over lower dimensional 2D space of chromaticities. For example, a computed spectrum representing the maximally saturated color red could simply be scaled to reproduce less saturated RGB colors, scaling with just pure red, some value 0 to 1 in the red channel and zeros otherwise. Spectra for highly saturated colors must necessarily peak within a small wavelength range to achieve this saturation, while less saturated colors can be represented by smoother spectra. It's generally preferable whenever possible due to inherent smoothness of reflecting spectra encountered in physical reality. Yeah. Okay. So, therefore, pre-compute a full 3D tabulation of each RGB color space that PBRT supports. That's the 4 there into a lookup table. Start up. Implementation of the optimization step is there in the source code, and in the further reading section, there's some more information. 4.30 shows plots of spectra corresponding to a few RGB values. So reflecting spectra represented by the RGB sigmoid polynomial of the RGB colors. 0.7, 0.5, 0.8 is the purple line, representing a purple color. So that's kind of what a spectral distribution for that color would look like. 0.25, 0.44, 0.33 is green. Curve for that, and then one for the brown line at 0.36, 0.275, 0.21. And so tables are stored in the binary. And they just index into it, I guess. Okay, so yeah, using an RGB, they can get a sigmoid polynomial thing. Okay, that's kind of the idea there. All right, so if the three RGB values are equal, it's useful to ensure that the return spectrum value is exactly constant. In some cases, a slight color shift may otherwise be evident if interpolated values from coefficient tables are used. Constant spectrum results C0 equals C1 equals 0. The approximate value of C2 can be found by inverting the sigmoid function. So it's as if all the channels are the same. So wait a second. Yeah, okay, it's continuous. Is the sigmoid function? Okay, sorry, I misunderstood before. The okay, they're separate curves for red, green, and blue. They're separate sigmoid curves for red, green, and blue. Okay, so these plots show the polynomial coefficients for corresponding XY chromaticities in the sRGB color space. For each of A, C0, B, C1, and C, C2 mostly very smoothly, though they do exhibit sharp transitions. Partitioning the gamut according to which of the red, green, or blue has the largest magnitude closely corresponds to these transitions. Coefficients are therefore independently tabularized in those three regions. Okay, so that's what they're talking about when you have these uniform things. Those are kind of like, yeah, when they're all the same or something. Yeah, so it's coefficients CI from the optimization are generally smoothly varying, with small changes in RGB generally leading to small changes in their values. This property also ends up being helpful for these in this goal. However, there are a few regions in the RGB space where they change rapidly, which makes direct 3D tabularization of them prone to error in those regions. The rest you just looked at. Better approach is to tabularize them independently based on which of the red, green, and blue RGB coefficients has the largest magnitude. Partitioning matches the coefficient discontinuities as well. So they end up with this thing in the section D. So, yeah, all right, 3D tabularization problem remains within each of the three partitions. Use the partition where the red component R has the greatest magnitude to explain how the table is indexed for a given RGB. First step is to compute a renormalization coordinate. By convention, the largest component is always mapped to Z. Similar remapping is applied if G or B is the maximum. With this mapping, all three coordinates span the range 0 to 1, which makes it possible to make better use of the samples in a fixed grid. And ever so slightly lost it. Trying to accomplish here. Okay, resolution is the same on all three dimensions because it's set to be a compile time constant. Changing size of the tables, compilation. Ay. All right. I didn't notice we had questions. Okay, yeah, so X and Z or something, yeah. I think, or no, the XYY one that they were talking about was the chromaticity thing. I'm not exactly sure what X and Z represent, X, Y, Z. I guess these are from like half an hour ago or more. So, sorry.